Imagine a future where the internet as we know it is transformed into an ultra-secure, lightning-fast quantum network. Sounds like science fiction, right? But this future is closer than you think. Scientists have just taken a giant leap forward by creating a scalable quantum node that seamlessly links light and matter. A breakthrough that could revolutionize communication, computing, and even timekeeping. Quantum networks are poised to redefine how we transmit information. Instead of relying on classical bits, they harness the power of photons to carry quantum information. This shift promises unparalleled security, the ability to merge distant quantum computers into a single supermachine, and precision sensing systems that can measure time and environmental conditions with mind-boggling accuracy. And this is the part most people miss. The backbone of these networks lies in quantum nodes, devices capable of storing and sharing quantum information via light particles. In a groundbreaking study, a team led by Ben Lanyon at the University of Innsbruck's Department of Experimental Physics demonstrated such a node using a string of 10 calcium ions in a prototype quantum computer. By meticulously manipulating electric fields, the ions were individually positioned within an optical cavity. There, a precisely tuned laser pulse coaxed the emission of a single photon, whose polarization became entangled with the ion state. But here's where it gets controversial. While earlier experiments could only link a handful of ion qubits to photons, this new method scales up dramatically, potentially handling hundreds of ions or more. Could this scalability finally bridge the gap between theoretical quantum networks and real-world applications? The process generated a stream of photons, each uniquely tied to a different ion qubit. In the future, these photons could act as messengers, establishing entanglement between distant quantum devices. The team achieved an impressive 92% ion-photon entanglement fidelity, a testament to the method's reliability. The scalability of this technique is its superpower, explains Lanyon. It opens the door to connecting entire quantum processors across laboratories or even continents. Marco Canteri, the study's lead author, emphasizes the broader implications. This isn't just a technical milestone. It's a stepping stone toward practical quantum applications. Think quantum secure communication, distributed quantum computing, and large-scale sensing systems. But here's a thought-provoking question. As we inch closer to these advancements, how will society adapt to a world where unhackable communication and unprecedented computational power become the norm? Beyond networking, this technology could also revolutionize optical atomic clocks, which are so precise they'd lose less than a second over the entire age of the universe. By linking these clocks via quantum networks, we could create a global timekeeping system of unmatched accuracy. And this is where it gets even more exciting. What other industries or fields could be transformed by this level of precision? Published in physical review letters and supported by the Austrian Science Fund FWF and the European Union, this work isn't just a scientific achievement, it's a cornerstone for the next generation of quantum technologies. But here's the real question. Are we ready for the quantum revolution? Let us know your thoughts in the comments. Do you see this as a game changer, or are there challenges we're not yet addressing?